Okay, so good evening everyone, and I think we should start right now our lecture. Basically, in the previous lecture, what we have talked about, we have learned about a direct and a compound nuclear reaction. And today's lecture, as I already told you in the previous lecture, okay, uh, we will talk about the quark model, right? So today, somewhat derivation, not derivation. I will not do any derivation right now, obviously, because previous class derivation was very boring things. So I will not do any derivation right now, and I will just do the simple basic things and the basic physics things about the quark model, as well as the elementary particle physics, you can say like that. So today, okay, I'm sharing my screen at first so that it will be visible for all of you. Actually, my internet is not that much good today, so maybe it will buffer. So I'm sorry at the very first of that. Is it visible to everyone, the screen?
Yes, ma'am.
Okay, thank you so much. Just a minute. Okay, so let's start. At first I am not going exactly directly to the quark model. I think you all know about the particle contents, like elementary particles, how many elementary particles are there, leptons, then hadrons, baryons. I think all of you know all the things, but still, like as a introductory portion, I am just telling some of these portions like little bit, and after that I will go to the quark model directly. Okay, someone is there. Okay, so okay. So today, I will talk about the elementary particles. Basically, elementary particles are so many elementary particles in nature right now. Like elementary particle means if you just tell someone that inside that atom what is there. So inside that atom you can say that inside the atom electron, proton and neutron is there. Among that electron, proton and neutron, obviously electron is the elementary particle, but proton and neutron is not the elementary particle. It is shown that inside that neutron and proton also there is something more, like some other particle is present inside that proton and neutron. So this type of particle is called that quark, which is present inside of that proton and neutron. I am only talking about proton and neutron, but there may be so many composite particles which is only made from the quarks. So basically, like if I just want to classify all the elementary particles or all the particles in nature, basically, then what will be the classification? The classification is I think you all know about these classifications, but still I am just writing a little bit. The classification means it will be at first on the basis of which statistics it will obey, like boson or fermion. Okay. So boson and fermion. So boson and fermion means the first one will obey the Bose-Einstein statistics, and the second one will obey the fermionic Fermi-Dirac statistics. So boson means it may be meson, it may be it basically boson means the integral spin will be there, and fermion means spin half particle or 3/2 something, like half integral spin will be there. So for bosons, like one of the boson is a meson. This meson is also like, if I just write here, I am not talking all the things here, like what are the types of bosons and what type of fermions are there in nature. All the particles I am not talking about. But I will talk about some more basic of bosons and some fermions. Like one boson I will talk about, which is known as meson, right? So meson, and for this is the boson criteria, like in that boson classification, meson is there, and the one is there, I will talk about that inside that fermion, there is known as baryon. So these two, like for inside, like in the classification of boson, meson is there, and in the classification of fermion, baryon is there. So just when we are talking about hadron, like why we are talking about hadron, I will tell little bit later. So hadron is nothing but meson plus baryon. Okay, so baryon as well as meson, which we call that as a classification. It's basically totally as a classification, like it's a classification for convenience, or you can say that in the classification based on the statistics, as well as in the classification based on the interactions, we can say all the things. So here if I write hadron, hadron is meson plus baryon. So why we are talking these meson and baryon as hadron? Because these hadrons basically follow the strong interaction. Okay, so if it follows the strong interaction, that means all the mesons as well as bosons inside, baryons inside that hadron will follow the strong interaction. So basically, if I will go about, if I will tell about quarks, then it will be obviously come that a strong interaction of quarks. So when we will go into the deep of that quark model, we have to know that which type of particles are made by quarks, right? So here basically mesons and baryons are basically made by quarks. So these are hadrons, and one more is there, the elementary particle, which is lepton. Okay, so hadron, that means meson and baryon, these are not the elementary particles, these are the, like it is, they are elementary particles, but fundamental particle is lepton and quark. Okay, so lepton is nothing but electron, proton and electron, muon and tau. Okay, and for the quark model, quark like mesons and baryons are totally composed by quarks, and quarks are another type of fundamental particle, just like the lepton. Like it is saying that it is assumed that there is nothing inside the quark, as well as there is nothing inside the lepton. These are the point like particle. So, but mesons and baryons, these particles are the composite particles. They can made by quarks. Now, these things are there. Okay, so mesons and baryon is there, but at first in the previous lecture, someone talked about that group theory, like why we are introducing group theory in the elementary particle lecture or elementary particle syllabus, and also why it is that much important for elementary particles. So for going into that portion, like I have just mentioned here that what is meson, what is baryon, what is hadron. Fine. Now, and also I have mentioned that what is lepton. Lepton, as an example of lepton, is electron, muon and tau. But why we are introducing in our particle physics theory the group theory, and why, like in what sense, in what extension group theory will be beneficiary for our particle physics course. Okay. So I will talk about this right now, that what is basically group theory. I think if you all might have known that what is a group theory, but I am not going to the details of group theory as a mathematician. I am just giving some basic things of group theory which will help in our particle physics. So what will help in our particle physics as a group theory, and why we are going to talk about group theory in particle physics. Like as you already shown here that there are so many particles and we have to classify these particles based on their interactions, or maybe based on their statistics, that which statistics they are followed, and all these things. So as we know that there are so many particles, like I think there are like like greater than 100 particles is there. So we have to classify these all the particles, and also just like the periodic table, you can say that just a minute, someone is there maybe. No, someone is not there. So okay. So basically, why we are using group theory in the elementary particle, to understand this question, we can think something about chemistry. In that chemistry, you have heard that a periodic table is there, right? So periodic table for what? Periodic table makes all the particles in a group wise thing, like all the atoms, all the molecules in a group wise thing. So just like that, we are going to make some group wise classification of for all the elementary particles in particle physics. So for doing that, we are taking some group theory concept from mathematics. We are not doing all the group theory in particle physics. We are just taking some of the group theory concept from mathematics in our particle physics. So what are these parameters and what are these group theory terms? The first group theory term is, let's say, SU2, and another is SU3, another is U1. These type of terms we have taken from the group theory from mathematics. So what is these things like SU2, SU3, U1? These all the things, and the main motto of that group theory in particle physics is that we have to classify our all the particles in such a way that we can understand each and every particle very clearly. That what is the property of these particles? Can we group so many particles in only one group? These type of questions will be answered by the group theory. Fine. So what is basically the group SU2, SU3, and U1? U is totally unitary. U is stands for the unitary, and S stands for what? S stands for special. So that means if I talk about SU2, that means the full form of SU2 will be special unitary or special unitary group of rank 2. In bracket 2, that means it is in rank 2. And SU3 means what? Special unitary group of rank 3. And what is U1? Obviously unitary group of rank 1, something like that. So special unitary, what are these? I will tell you. So special is nothing but it's not that much special. The special is in the sense that the determinant of that group, like in that group there are so many elements. So each and every element, if it form a matrix, then the determinant of that matrix will be +1. So this type of condition will give us a special condition. So if the special unitary will be there, then the determinant of that elements matrix will be +1. So nothing more than that. And rank 2, rank 3, and all these things is there. So so why we are taking only these 3 things here? So if I just take some example of particle physics, then you can easily understand that why we are taking SU2, SU3, U1 here in our particle physics. So let's talk about one very simple example, that proton and neutron. We all know that what is proton and neutron. Proton and neutron are the composite particle of quark, but we are not talking about quark right now. But we are talking about as a particle that P and N are 2 particles, and which are present inside the nucleus. Fine. So proton and neutron is there, and we all know these things also, that proton and neutron are making a doublet. Okay, like why it is a doublet, and proton and neutron, these two are these two are compositely called as nucleon. So, and the mass of the proton and the mass of the neutron are very similar, like there is very percentage, like 2 or 3% difference in between the proton and neutron mass. So proton and neutron are very similar, and we are taking these two particles as a very same footing, like we all called this proton and neutron as a nucleon. So nucleon means it may be a very similar thing, like proton and neutron have the same properties and all these things. So we are taking these things in a equal footing. Okay, so if I just take proton and neutron, then it may be possible that we can group proton and neutron in one group. Like we are right now, what we are doing, we are grouping all the particles in such a way that they can express their all the properties very similarly, just like the periodic table. I think you all know that in periodic table all the column wise particles gives the same properties and chemical properties and all these things. So just similar like that, we are going to group these all the elementary particles. So here if I just want to group proton and neutron in only one group, then it will be a group. Okay, so what will be the group? This group, like if I just taking as a equal footing of proton and neutron, then proton and neutron will make a doublet. Doublet means, like if I just write here proton and neutron, these two particles can form one quantum mechanical state where two state is there, one is proton and another is neutron. So this type of combination can be taken as a doublet form, and this doublet form will be characterized by some properties. Some properties means this P and N, if I take as a doublet, then it will form as a SU2 doublet. So why SU2 doublet? Because like if I write here proton and neutron, you know that proton and neutron, for the proton and neutron isospin is what? For proton and neutron isospin is half, right? And if I write the third component of isospin, then for proton the third component of isospin is plus half, and for neutron the third component of isospin is minus half. So if I just make a group for proton and neutron in the basis of isospin, then we can group proton and neutron as a similar footing, because these both have I equals to half. So if I write I equals to half, then we have I equals to half means, okay, proton and neutron is there because plus half for proton and minus half for neutron, and these two can make a doublet. This doublet can be grouped as a, like these two particles can be grouped in a specific manner. Fine. So this type of example will be there, that proton and neutron can be grouped in a group, because there are so many similarity between proton and neutron, as well as there are these two particles have same isospin and all these things. So now let's say if I write here, let's say two composite particle, like two doublet is there. Two doublet means like one has plus half and one is minus half. This is one doublet. Now I am writing here in terms of I3. This is one doublet, and let's say another doublet is there which is plus half and minus half. So these two doublets is there. Now it may be possible that we don't know that inside that particle what is there. Okay, so it may be possible that these two doublet will combine. If these two doublet will combine, then how we can write mathematically these things? That this is doublet, that means we can write it as 2, and this is also a doublet, so we can write it as a 2. and there will be a combination. For that combination, the SU2 combination is there, so that means it's a tensor product. So we are writing here cross and then a circle. Then what will happen? The answer will be like 3, then plus, then circle and 1. So 3 is what and 1 is what? Like this expression, that 2 cross 2 equals to 3 plus 1, this mathematical expression says us that there from 2 isospin doublet we can get 1 triplet and 1 singlet. So how can we find these things? Like how can we form this 3 plus 1 from 2 cos 2? This is basically whatever I have written here, that 2 cross 2 equals to 3 plus 1. This is basically a property of SU2. So this is a mathematical expression that 2 cross 2 equals to 3 plus 1. But how can I form these things in physics, and how can I visualize this? So it's a very simple thing. Very simple thing means what? If I just write here 2 doublet is there, right? So 2 doublet is there. So 2 doublet is there means I am writing here 2 doublet minus half. These things are called basically weight diagram, and plus half. Okay. So this is 0. So there is I am writing 1 doublet as minus half, plus half, in between that a 0, a point like thing. So another doublet is there, another doublet was what? That minus half and plus half, and there is 0. So these 2 doublet is there. Now what will happen? These two doublet will superpose with each other, so that we can have 3 plus 1. As I already mentioned that this is not a simple multiplication, this is a tensor multiplication. That means what? The tensor multiplication is like that. See, this minus half of that second particle will come here, and it will do like with that minus half and this minus half. Like it will interact with both the doublet. Then what will happen? Both the component of that doublet. Then what will happen? The resultant will be here minus 1, and here the resultant will be 0. Now for the another combination, that plus half will come here, as well as plus half will come here. So minus half was previously, and right now the plus half is there, so that means as a whole 0. And here plus half was initially, and here plus half is also coming, so as a whole 1. So that means as a output, what will be the result of that composition? Minus 1 is there. See, here is minus 1, here is 0, here is 0, and here is 1. So that means minus 1, 0, 1. We can group these 3 as a triplet and 1, 0 as a singlet. So 2 cross 2 can make 3 plus 1. So this type of things comes from the gauge group theory. Now these type of things are important in which condition, in which situation we will talk. But here basically I am just talking this SU2. But in our quark model, or in our baryon, hadron and meson model, we are not talking about SU2. We will go more extension of SU2. We will just talk about SU3. So SU3 is what? SU2 is like what? That SU2 shows all the possible combination of same isospin multiplet. Okay, so same isospin multiplet means like if I equals to 2, then I3 will be plus half and minus half, and it will be determined, and these 2 plus half and minus half will be very similar in mass and very similar in nature also. This type of condition will give the SU2 contribution. This type of condition will come from the SU2 configuration. So right now we are going to do something more about SU3, because in our nature SU2 is very less, SU3 is very normal and very natural. So in SU3 combination, let's say SU3. So SU3 combination, in this combination what will be there? In SU2 I have told you that I will be same, right? Like as P and N I have taken as a example. But here in SU3 I will be same, that is fine. But Y will also be same. I think you all know that Y, what is Y? Y is the hypercharge. So Y and I will be same if that type of particles are there. Like there are so many, there may be so many particles which have same I, same Y, then this type of particles we have to figure out by the expressions given by SU3 group theory, and we have to say that each and every particle coming from the same I and same Y has very similar mass and very similar nuclear nature. So like SU3 gives us I and Y same, as I already told. So I and Y same, that is fine. But how can I see that I and Y is same? And also, what is the mathematical expression for SU3? Mathematical expression for SU3 is like that. If I write 3 cross 3, then what will happen? Then 3 cross 3, basically in mathematics, simple mathematics, if I do, then 3 cross 3 will have 9. Obviously you all know that. But it will be in a tensor form, then it will give us 8 plus 1. And if I do another mathematical conclusion, then 3 cross 3 cross 3, then it will give 27, which will give us 10 plus 8 plus 1, and this plus with circle, this is a tensor product. Like tensor addition and tensor product is for circle, and in between that circle cross is there. So this type of thing will be there. So I am taking one example for that, so that it will be very much understandable by you. One example will be like, if I write here that baryons, like this type of example. See, Y equals to this. This is the hypercharge expression. So I am not writing right now here this one. See, this is Y and this is I3. I am plotting I3. Okay. So for that SU3 combination, I was talking about that same Y and I. But right now I am talking about here I3 plot. So I know you all have seen this type of graph before also. So in that Y and I3 set, then what will happen? This type of, if I write here one octet, yes. So what is there? There is, like, it is as I already told you that hadrons will made with the meson as well as baryon. So if I write here that meson will give that type of symmetry in Y and I3 graph, as well as for baryons also, if I write Y and I3, this type of symmetry will be there. Is there any question? Like, if you people have any doubt, then you can just ask me. Otherwise we will move. That if I write here that Y versus I3, then it is for baryon if I write, and this is for meson. Okay. So this type of symmetry will be there, and this type of symmetry will come from what condition? That it will come from 3 cross 3 equals to 8 plus 1. And I will show you in quark condition that how this type of expression will come. Okay, like how octet will come, as well as for baryon decuplet is also coming. So how this type of terms will come in a quark model, I will also show you after some time. So here also 3 cross 3 equals to 8 plus 1. This type of condition will be here. Now coming to the quark model, like if I just do these things in on the basis of simple composite particles, then I think it may be not that much good. So I will do the quark model what you people suggested me. So right now, quark condition. So all the things whatever I have written here, that this type of things is there. So for that meson things means what I have written here, all the particles, like each and every corner there is one meson. Here. So here these two is like 1 2 3 4 5 6. So that means 6 meson will be at each and every corner, and in the center there will be two particles. For meson I think it is pi 0 and eta 0. So which will make a 8 particle symmetry, that means octet symmetry will be there, and one singlet will be there. This singlet is nothing but that eta prime. So I will tell that how these things has come in the context of quark. And here that for baryon also there is proton, neutron, sigma minus, sigma 0, sigma plus, and then cascaded minus, cascade 0. And there is also one state which is lambda 0. These a whole 8 particles will give us 8 octet. Like 3 cross 3 it will gives 8. So now okay, so this type of particle is there, and here if I just write something k plus, k minus, I totally forgot these things, like what type of particles will be there. So if I just calculate here y value and I3 value, then we can find each and everyone's charge also. The charge can be written as this expression, I3 plus y by 2. So after coming to that expression, we can have each and every particle's q value, and we can see that here y and I3 value is there. And okay, and one more thing is that in that graph, here this particle, these two particles has same mass. It should be same mass. Okay, so here as I already told you, for baryon the particles are like proton and neutron, and here is I3 value and here is y value. So if it is plus 1, and for proton it is minus of, it should be neutron and proton, and minus half and plus half. So you can see that plus half, minus half, these two I3 value will give 1 I equals to half. So this same I value as well as the same y value, that means y equals to half and y equals to plus 1. This gives a symmetry that this is a group. Okay, so we have grouped these two particles in such a group that we can see that proton and neutron has a very similar mass. And also just same like proton and neutron, sigma minus, sigma 0 and sigma plus is there. So for these cases, sigma minus is minus 1, sigma 0 and sigma plus 1. So here I equals to 1 and y equals to 0. So that means for y equals to 0 and I equals to 1, that type of combination, we can have 3 particles, sigma minus, sigma 0 and sigma plus. Both should, these 3 should have similar masses, and that's why we are putting these 3 particles as a same footing, as a equal footing. Okay, so just like that one also, there is a cascaded minus and cascaded 0. These all have, I think, I equals to half and y equals to minus 1. So this type of things is there. And also here lambda 0 is there. So that means sigma minus, sigma 0, sigma plus, these 3 will give a triplet, and lambda 0 is in between that, which will give a singlet. So like after seeing this type of symmetry is obviously coming from the group, like group theory, whatever you have said, that SU3. This SU3 group theory gives us that type of symmetry, that we can have a octet like symmetry in our particle physics theory, which will give us grouping of all some of the particles in one group, some of the particles in another group. That type of grouping will be there, just like the periodic table we are doing here, a grouping of all the particles in such a way that we can have a grouping for all the particles very conveniently. So for baryon it is like that, for meson the same things are like that, but only the particle combination is different, like here k plus k minus and all these things will be there. And okay, this type of things is there. So basically as I already told so many times, that group theory is nothing that much worried in particle physics. It's totally based on a convenient of our grouping, that it will help us in grouping all the elementary particles in such a way that we can conveniently see all the particles in a table form or in a grouping form. So if I just write here the quark content of all these particles, then it will be very useful for making this y and I3 plot. So if and also the docuplate is also there. I have not shown you this one, y I3, and docuplate means this type of graph will be there. So in that docuplate, what will be there? Docuplate means 10 particles will be there, and 10 particles in that type of symmetry is there as a docuplate symmetry. So this type of things is there. Now if I just write the quark contents means, like quark means right now there are 6 quarks, but at the time when we have talked about these octet, docuplate, meson octet, baryon docuplate, baryon octet, all the things, there was only 3 quarks. 3 quarks means who are they? The quarks are U, D and S. So U, D and S, these 3 quarks were there, and U for up, D for down, S for strange. And in among these 3 quarks, we are also grouping these U and D as U, D as a doublet and S as a singlet. And for the UD, the strangeness quantum number is 0, and for S, the strangeness quantum number is -1. Okay. So there is at that time.
Hello, ma'am.
Yes.
Uh, how does we arrange 10 particle on docuplet?
Okay, how does we arrange? Just a minute. I can't hear all the, I think my internet. Okay. Can you tell, like, how does the?
How does we arrange 10 particle in docuplet?
Okay, so in docuplate, just similar as octet, the docuplate will have a yi3 graph. Okay, in that yi3 graph, there, let's say here I3 is -3/2, minus, what will be 2, sorry, -1, minus half, 0, half, this type of things, 1, 3/2. So here we are taking I3, and also for docuplate JP value will be 3/2 plus. So that means whatever the particle inside the docuplate, they all obey the JP, that means spin parity, as 3/2 plus. Fine. So now for the y value will be like a minus +1, 0, -1 and -2. So if I write y value as well as I3 value, then we can have that type of graph here. Yes. So here what will be there? Here delta plus, delta minus, delta 0, delta plus, and then delta plus plus. This is plus plus. So these 4 particle will be there. Why this 4 particle is there? Because here if I just take this line, okay, so in this line I3 has value minus 3 by 2 to plus 3 by 2. So minus 3, so that means delta minus has I3 value is minus 3 by 2, delta 0 has minus half, delta plus has plus half, and delta plus plus has 3 by 2. So that means it's a like it will give a like quadruplet, like 4 particle in a group. Okay, so and all has the same y, same I. Y has 1 and I has 3 by 2. Now this line has completed, and right now we are going to this line, 0 line. Yeah, here in that line what will happen? Sigma minus sigma 0 sigma plus, because here minus 1 is there, I3 0 and plus 1. So these 3 will have the same I value as well as 1 y value is 0, same for all the particles, sigma minus sigma 0 sigma plus. And what is there? Yeah, there here cascaded minus and cascade 0. And what is there? There is omega minus. So like taking all the s values and b values, we are calculating y value for each and every particle, and for each and every particle we are also calculating I3 value. Just putting this value in this graph, we can have that type of docuplate. Understand? Hello?
Yes, ma'am. Understand.
Yeah.
And the mass will be the same in the same all
Same line.
deltas mass have the same.
Same line, like here, like sigma z, sigma minus, sigma 0, sigma plus, these 3 will have same mass. Like basically it should have same mass, but due to the electromagnetic interaction, like you all can know that sigma minus has minus 1 charge, sigma 0 is 0 charge, and sigma plus is plus 1 charge. So that means there is a difference between electromagnetic interactions. So due to the electromagnetic interaction, there is some mass splitting, but like in the concept of strong interactions, all the particles should have same mass. But as there is a different charges for each and every particles, the electromagnetic interaction will give a mass splitting between these particles. But we are not talking about electromagnetic interaction here, we are just talking about strong interaction. So that means in the basis of strong interaction, all the particles sigma minus, sigma 0, sigma plus should have the same mass. Okay.
Okay, ma'am.
Yeah. And also for that similar cases, delta minus, delta 0, delta plus plus, and cascade minus, cascade 0, these things have the same mass. And also some predictions is also there. There's some predictions from that SU3 group is there. I'm taking the predictions like, yeah, this one. If I just write here the octet, I'm just taking the octet condition. Okay, so this octet condition is there. This is neutron, this is proton, sigma minus, sigma 0, sigma plus, and this is cascade minus, cascade 0, and this is I3 value, and this is y value. And what is the Jp value for that? Jp is half plus. Okay, like I am writing here, Jp value means spin parity value. So for all the particles, spin parity is same. That's why it is grouping like that. Okay. So now the property of SU3 is like that. As I already told you that the line, the same line, whatever the particle is there, they should have the same masses. And one more prediction is there. Let's say Mn plus M. Sorry. Cascade 0, which will equals to M sigma 0 plus M lambda 0 3 into lambda 0 by 2. So what is this means here? That Mn, this mass plus the cascade 0 mass, these two masses is basically very equals to, here is lambda 0, I already told you that sigma 0 and lambda 0 has the same y and I3 value. So these two masses, the addition of these two masses will be equal to m of sigma 0 plus 3 into m of lambda 0 divided by 2. This is a prediction coming from the SU3 group, and it should be there, and obviously experimentally if I just calculate all the values of all the masses of all the particles, then it is there. Okay, and the another more condition is there. Another condition is very simple. Another condition is this one: mn minus mp plus m cascade minus m cascade 0 equals to m of sigma minus m of sigma plus. What does it mean? It means that if I just, okay, yeah, here I am just taking little bit smaller. Here you can see that mn minus mp, that mass difference between these two particles, and if I just add the mass difference between cascade minus and cascade 0, these two mass difference, I am just adding these two, it will be equal to the mass difference between sigma minus and sigma plus. It is the another prediction of SU3 group from here, from that type of octet. Okay. So this type of prediction is there. Now okay, now if I just write here for docu plate, the same thing will happen. For the docu plate, delta minus, here what is that, sigma minus, cascade minus, and omega minus. So for the docu plate, what is the condition is given? The condition is m of delta minus m of sigma minus equals to m of sigma minus m of cascade minus equals to m of cascade minus m of omega minus. So can you explain what does this means? Can anyone? Like why? What does this means that delta minus sigma minus this type of things obeys this type of conditions?
I think mass is decreasing.
Mass is decreasing, that is fine, as well as the mass difference between these two lines is same. Like if I go from first line to second line, then the mass difference whatever it will be, from second line to third line the mass difference will be same.
Oh.
Yeah, like as
Yes,
you can
yes.
see that this one, if I just write here first line, this one is the second line. Actually this type of line will not be there, but for convenient I am taking that type of line, and also this third line is there, fourth line is there. So this mass difference is similar, same as this difference, and this difference is also same.
That means equally spaced
Equally spaced,
in the
right?
sense
Yeah,
of mass difference.
yeah, right. So the like mass difference will be equally spaced, that is right. So this type of things will be there, and obviously whatever the predictions coming from the SU3 group, obviously it is experimentally verified that there is indeed some mass difference, and this mass difference is equal to 1 between 1 and 2 and 2 and 3 and 3 and 4. But there may be some experimental error, 1 or 2%, not more than 5%. Okay, so this type of things is there. So these whatever I have just told you right now, these type of things are like octet, docuplate, for meson, baryon. For mesons is also that this type of condition is valid. I am just taking that n and p, that it is not that it is only for applicable for n and p only. It is also applicable for mesons, that as I already told you that mesons is also compose, like meson is also can be grouped as a octet. So that means meson can also be put in spite instead of that n and p and all these things. Okay, so now that if I just write these octet as well as decuplet in the quark containment, that's a, let's say, quark. So in that quark, what is quark here? U, D and S. So U, D and S, the U has the charge 2 by 3, D and S has charge minus 1 by 3, and U has strangeness number 0, D has also strangeness 0, and S has strangeness minus 1. So if I write here U and D as a doublet and S as a singlet. Fine. Now if I just write here all the things whatever I have written there, that 3 cross 3 or 3 cross 3 cross 3, all the things if I write in terms of quark, then what will happen here? So let's say, okay, so for meson and baryon, for meson the quarks are like U, Q, Q bar, and for baryon Q, Q, Q. Why that type of things is there? Because meson is spin 0, 1, 2, something like that, and baryon has spin half, 3 by 2, 5 by 2, something. So if and also quark has spin half particle, it is a spin half particle and it is indeed a Fermi particle. Okay, so that means if I get spin equals to 0, 1, 2, that means only integral spin, we have to take a q bar like thing, because if I take q, then obviously it should be a half integral value, it should give a half integral value. So that's why for meson q bar will be there, and for baryon q type of things will be there. Now what is q bar here? Q bar is basically the antiparticle of q, and q I am denoting q as a quark. So now let's do one thing. Q as U, D, S, fine, and Q bar is U bar, D bar, S bar. Now for the octet case, means this case, I want to formulate this expression in terms of quark. Then what will be there? The things will be U, D, S is there, and let's say U bar, D bar, S bar is there. So here 3 means U, D, S, that triplet is there, and another 3 is like U bar, D bar, S bar, this type of triplet is there. So as I already told you, in the case of 2 cross 2 equals to 3 plus 1, just similar like that we are going to do here. So what we will do here, I am just writing I am not giving the weight diagram here, I am just writing the expressions what will be the composite value of U, D, S after 3 cross 3 equals to 8 plus 1. So after 3 plus 3 means U, D, S. Let's take at first 1 U. So this U will go U bar, U, D bar, U, S bar. Fine. Then come to the D U bar, D bar, D, S bar. Then coming to the S U bar, S, D bar, S bar. So this type of composite particle will be there. So how many particles, composite states are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 composite states. 9 states is there, right? So for among that 9 states, if I write here U, D bar, U, S bar, D, U bar, D, S bar, S, U bar, S, D bar, 1, 2, 3, 4, 5, 6. These 6 combination will place at the 6 vertices, and another combination u bar plus d bar plus s bar. This combination will be inside that octet, like here as I mentioned here about the meson, so that means it will be pi 0 or eta 0. So this type of contribution will be for pi 0 and eta 0, and this type of contribution will be for each and every particle at the corner of that octet state. Is it understandable? Hello?
Yeah, yes, ma'am.
Okay, yeah. So that means if I just do here 3 cross 3 equals to 8 plus 1. Okay, now 8 I have made here. How 8 have made? This 6 was there each and every corner, and here these two condition will give 2 particles, so that means 8 particle is there. So that means 8 state is already formed by this is 8, but where this 1 is there, so 1 is basically nothing but the another eta prime particle which has the same configuration, same quark configuration, that u bar plus d bar plus s bar, but the difference between eta prime and eta 0 and pi 0 is that it comes from the color combination. So I will not talking right now the color combination here, that color combination will come from the quantum chromodynamics things. So right now you can see that there is a 8 configuration inside that octet, and another one, that means the singlet, will come from that eta prime configuration, which has the quark configuration as u bar plus d bar plus s bar. So this is for the, okay, I don't have any charge, just wait. Oh shit. So this is for octet state. Now if I just come to the, and it is obviously for the meson because we were talking about q bar, but if I talking about baryon, that q, that means for q there may be one doppler, that two possibility was there, 3 cross 3 equals to 8 plus 1 for baryon is also possible, and also 3 cross 3 cross 3 equals to 10 plus 8 plus 8 plus 1. So these three conditions will be there. So then how it will come, like here as if I calculate 3 cross 3 cross 3, so that means what will happen here, 27 state will be there, and 27 state can be divided in that way, that 10 plus 8 plus 8 plus 1. So if I calculate all the 27 states here, then it will be a tedious work, but still I am doing. Okay. So just similar to that UDS case, I am taking UDS and UDS. Fine. Then first U, and also if here we were talking about Q, so that means there will be no Q bar here. So that means no bar condition will be there, only UDS and UTS will be there. So if I superimpose these two Q states, that means first line and second line, if I impose these two conditions, then what will be the resultant? The resultant will be like UU, UD, US, DU, DD, DS, SU, SD and SS. this 9 condition will be there. Okay, like if I just it superimpose two q states, now the third q is also there. So third q means what? This you will superimpose with these whole 9 states, one which will give 9 another state, and then d will also superimpose to that 9 component, this will give another 9 state, and this s will give like superimpose to these all the 9 components, this will give another 9 components. That means 9 states will be there as a whole. 9 into 3, that means 27 state will be there. So if I just write this 27 then it will be very big, but still I am trying to write. See what I am doing here. At first I am taking this u and I am multiplying this u with all the 9 states here. So nothing is there, u d, and like, okay, I am writing here u d u, u d d, UDH, USU, USD, USS. Fine. This is the first 9 state. Now what we will do? We will do the D. Here is the D, and we have to multiply this D with this 9 component. Then there will be another 9 component, and if I just multiply S with this 9 component, there will be another 9 component. So that means total 27 states will be there. So okay, if I am writing this, then maybe DUD, DUS, DDU, DDD, DDS, and then DSU, DSD, DSS. Now what will happen? We are going to multiply this with S. So that means SU.
Ma'am, hello ma'am.
Yes, yes.
You can skip this.
Yeah, it's a very long thing. Okay. Yeah.
Yes.
So that means like I think you all know that how 27 states are coming. Okay. So
Yes,
this
yes,
type of things, by calculating this type of things, 27. Okay. 27 states are coming. So after coming that 27 conditions, then we have to make this docuplate, right? Because we have to calculate that in the context of quark. So we have to make this docuplate. So in that docuplate, what is there? Y is there and I3 is there. So here here 10 as docuplates means what? 10 docuplates means 10 particles will be there, but there is 27 state. So 27 state cannot give a 10. Like obviously 27 means some portion will give for 10, some portion will give for 8 and 1. Okay, so this 10, this how we can find this 10 in the quark concept. This 10 will give like this type of things, that say here 27 condition means I am taking some of the conditions here. This u where is that? Okay, this u will put here, not here, here u, and here u d, here u d d. But basically how I can write these things? I am writing these things like that because when we will go from left to right, our u will go as, sorry, our d will transform as u. See here u dd was there, then in that next step what was there? 1d has transformed into u. Then what has happened? This last d has transformed into 1u. So that means as a whole u is there at the very last position. And when the conclusion from these type of things is that if I am present here, if I go left to right, 1d will convert to u, and if I go from up to bottom, 1d will convert to s, and it should be there because we have y and I3 value in such a way that if I go from left to right, d will convert it to u, and if I go from up to bottom, d will convert to s. And then what will be there at the very last point? At the very last point means this point. This point will be s, because it is at the very last point. So that and which is nothing but omega minus particle. And I am not writing all of the particle contents in the quark contents configuration, but this type of things will be made. yi3. So among the 27, some states will give a Doppler condition, Doppler symmetry. Some state will give octet condition, some state will give another octet, and some state will give one singlet, so that we can have 10 plus 8 plus 8 plus 1. Is it fine?
Yeah, yes, ma'am.
Okay. So in the concept of quark model, we can say that each and every u, d and s, whatever I have written here, octet as well as decuplet, these all are made with only 3 quark, u, d and s. But obviously after some time in the late 90s and the first 21st and 20th century, we have found another 3 quarks which is known as charm, top and bottom. Sorry, it should be B. These 3 quark we have found, but we were doing all the things here in the concept of only 3 quark, u, d and s. We were not talking about C, T and B, but when we have a very large energy in our experiment, we can also find C, T and B type of quarks, which will also present in our quantum electrodynamics or QCD theory. Okay, so I think the time has over. In the next class we will tell about the color thing, like quantum in that quantum chromodynamics, what is there, color charge, color field, gluon, what is gluon, how the gluon will interact with all the particles, and also what we will say, okay, and also why meson is q bar and q is baryon, and how the color concept has come. We will see all these things in the next class. Okay, like why q is there, and why we should introduce color charge in the particle physics in quantum chromodynamics, and what is basically gluon, and what is the states for each and every gluons. So we will tell all the things in the next class. So if there is any question, please let me tell. I will answer these questions. And if there is no question, then we can.
How can we identify the isospin triplets?
Isospin triplet, how can we identify? Okay, see, if in that grouping, whatever I have told you, that group like thing, so if in that group like sigma plus, sigma 0, sigma minus is there, so that means three members are in a group. So 3 members are in a group, that means as I know that 2i plus 1, sorry, 2i plus 1, 2i plus 1 equals to 3, so that means I equals to 1. In that condition we can say, like and also you can go reversely, that if I equals to 0, then there will be 3 members, and 3 members means each and every one will be minus I2 plus I, like each and every one will have the I3 value minus I2 plus I value in the step of 1. So that means minus 1, 0 and plus 1. This 3 will be there and I3, so that means 3 particle will be there, 3 state will be there, and 3 members will be in that same isospin. If the triplet is there, that means 3 particles will be there, and in the 3 particle state I should be 1, because 2i plus 1 equals to the number of members present in that group.
That means the triplet means only three state.
Triplet means 3, doublet means 2. So if I take doublet, that means 2 members will be there. So as I know, 2 members is there and 2i plus 1 is the expression. So after calculating this, what will be the value of I will be half. Then like if I know the doublet, triplet or quadruplet, whatever it is, we can find the value of I. In that value of I, from that value of I, we can also find the I3 value for each and every particle. Like only I equals to half means 1 will be minus half, 1 will be plus half. Because I3 have the value, I3 should have the value minus I2 plus I in between the step of 1. So if I equals to half, that means I minus half and plus half, and minus half and plus half, in between that obviously one step is there, so that means no more state will be there. So 2 state will be there, one is minus half and one is plus half. And as a doublet is there, that means doublet means 2 particle will be there. So for that 2 particle, one particle will have I3 equals to minus half and another particle will have I3 equals to plus half.
Does
Okay,
they
ma'am.
need to be from the same group?
Yeah,
Do they need to be from the same group?
same group, like yeah, like I see I
Like
equals,
sigma minus, sigma naught, and sigma plus.
sorry, hello.
Yeah, like they need to form or not to form the isospin triplet. To form the isospin, it needs to be the same group.
Yes, like same group means same I value will be there. As same I value means that same number of nature is there, same nature is there between all the particles, and it should be in the SU2 symmetry form. Like in the SU2 symmetry, same I value gives that same particles is there. Same particles means number of particles in is, like number of particles, like 3 or 4 number of particles can be grouped as a group. So and which have the same I value, same isospin as well as same Y value. For SU3, for SU2 case only spin as same isospin is there. For SU3, I and Y will be same. For SU2, I will be same. Okay, but
Thank you, ma'am. Thank you.
yeah, but in a nature SU3 is more likely than SU2. That's why we are talking octet, decuplet and all the particle content in basis of SU3, not in the basis of SU2. But if I write only P and N condition, proton and neutron condition, then we can write in basis of SU2, because there is only 2 particle and we are making these 2 particle as a doublet in the basis of SU2, because the same isospin is there. Okay. Okay, so that means like today itself the quark model, like quark model is a little bit there, but if you want to know quantum chromodynamics, then we have to shift to the next class also. So in the next class we will talk about quantum chromodynamics, like how color is coming in the picture, and why color is that much important, how gluon has color, and how it is interacting with the particles. All the things will be there. Okay,
Oh, okay, ma'am.
bye bye.
Okay, ma'am. Thank you. Bye.
Bye, ma'am.